Hello everyone! This is the first of a series of videos dedicated to infrared spectroscopy. In these videos we will be looking at the scientific basis of infrared spectroscopy, and we will learn how an infrared spectrometer works. We will also discuss some of the strengths and limitations of infrared spectroscopy. Finally, we will see how we can identify functional groups in an infrared spectrum, and we will learn how to interpret infrared spectra of simple molecules. And when I say simple molecules, I don't mean that they are easy to interpret. What I mean is that they are small molecules with just a few atoms, or as opposed to, for example, large molecules such as proteins. Infrared spectroscopy is a hugely popular technique. Can be used in a chemistry laboratory to quickly identify a substance, or at least to give us an inkling of what the substance can be on the basis of bands in the infrared spectrum. It's also widely used routinely in forensics, for example, to identify paints, fibers, or drugs, as well as various other industries, from, for example, jewelry to identify the quality of gemstones, to food quality to identify adulterated products. Here is just a couple of examples of the use of infrared spectroscopy in current research. This paper from 2019 talks about how infrared spectroscopy, Fourier transform infrared spectroscopy, which is the technique we're going to be discussing in these videos, to identify adulterated milk by identifying the compound melamine in milk. This is a fascinating technique from 2019 in which the researchers use a specific type of infrared spectroscopy called ATR, attenuated reflectance, to study, to detect brain cancer by analyzing blood samples from the patients, and in the basis of their infrared spectrum, reveal the early signs of particular brain tumors. Infrared spectroscopy is a specific type of a larger variety of spectrometric techniques called molecular spectroscopy. Molecular spectroscopy focuses in the transitions between energy levels within atoms and molecules, and those energy transitions, can be recorded and will give us information on the chemical structure of that particular compound. In the case of infrared spectroscopy, what we are looking at is vibrational molecular spectroscopy. We are identifying compounds on the basis of how they vibrate and how the atoms vibrate, and that will translate in an infrared signature that we are able to detect. The energy range used in molecular spectroscopy is very large, and it spans a very large range, a very large proportion of the electromagnetic spectrum. And here highlighted some of the key ones that we use: UV spectroscopy, visible spectroscopy, and infrared spectroscopy, which is what we are looking at in these videos. Infrared radiation is capable of exciting molecules and make them vibrate and change their vibration patterns, and that's what we can detect when we use an infrared spectrometer. As I mentioned before, infrared spectroscopy is one type of molecular spectroscopy, and in molecular spectroscopy, molecules will go to a higher energy level, to a higher energy state, by absorbing radiations of the appropriate wavelength. The absorption will only happen when the energy provided by the radiation is enough to match a particular energy gap between two energy levels. In that case, the molecule will absorb the energy and will reach an activated state. And if there are different upper levels, different energy levels that can be achieved, then several transitions will be observed. The infrared radiation part of the electromagnetic spectrum will induce a stronger molecular vibrations in the molecules. So when you have a covalent bond, it's sometimes useful not to think of it as a rigid structure, but think of it as two masses, two atoms bonded together by a spring. And the spring will be different. That imaginary spring will be different depending on the atoms that are making that bond. And with the right wavelength of infrared radiation, it is you are able to excite that spring, so the vibrations are stronger. And if you look at this, the diagram in this slide, you can see what would be the bond with no energy applied, in equilibrium, vibrating at a particular frequency or with a particular force. And then when infrared radiation of the right wavelength passes through the bond, it's able to change the way the bond vibrates, and that can be detected. That is what is detected in an infrared spectrum. There are different ways a molecule or a set of atoms bonded together by bonds can vibrate that will cause absorptions in the infrared region. The main modes a molecule or a set of atoms can vibrate is by stretching or by bending. In the diagram you have here, you have an example of stretching modes, the ones at the top, and the stretching can be symmetric or asymmetric. And there are also bending modes in which they involve 3 atoms, and the 2 atoms in the end of the bonds bend with respect to each other. And there are 2 types of bending mode, the rocking mode and the scissoring mode. And as you can see from the diagrams, they're slightly different. So stretching modes, symmetric and asymmetric, and bending modes, rocking and scissoring. This is an schematic diagram of how an infrared spectrometer looks like. You have an infrared source that produces the infrared radiation. The infrared radiation goes through the sample. Some of the wavelengths of the infrared radiation that go through the sample will be absorbed. They will be able by the bonds, and they will be able to elicit a particular stretching or bending modes. And the rest, the ones that do not have the right energy to bridge an energy gap, will go through. So an infrared detect, and then that you end up with the outcome of that is detected, and the infrared detector measures what frequencies of infrared radiation have gone through, and by default it will tell you which ones have been absorbed, which frequencies have been absorbed by the sample. So in that way, you get information about the chemical sample by knowing which wavelengths have been transmitted and which ones have been absorbed by the sample. And those infrared frequencies will depend on the structure of the sample and the bonds that sample has.